Hello everyone, my name is Alec Shamula, and today I'll be discussing my research on dynamic weight allocation for logistic regression using Bayesian networks. I want to start by providing an outline of what can be expected from this presentation. So first we'll be covering an overview. This will give the mission statement as well as the motivation for this research. Next we'll be providing some necessary background. Following that, we'll discuss the methodology of the proposed approach, and then we'll spend some time covering the data set at length. Following that, we'll discuss the results from this study. Then there's some further discussion points that I want to discuss, and lastly, we'll end on a conclusion, just covering some of the main points from the study. So let's begin by discussing what this research is actually about. This research aims to improve upon traditional logistic regression by allowing for dynamic weight adjustments where weights are inferred by an underlying Bayesian network based on instantiations of the input feature. So what does this actually mean? Well, during training time, we're going to be using information that comes from the logistic regression model to actually update the Bayesian network, and specifically update the probabilities, the conditional probabilities inside the Bayesian network. Then at inference time, we use the Bayesian network and the conditional probabilities learned to infer what would be the best weights based on instantiated values for the input features. We'll be discussing this at more length, but I just wanted to give a brief overview of what the goal of this research is and what the algorithm is attempting to do. And so the motivation for this is to overcome some of the limitations of logistic regression. One of those limitations, for example, is the ability to classify non-linearly separable data. We'll discuss this at further length, but we will see that this is actually a weak point of traditional logistic regression models. And this research is looking to find a way to improve upon that. So I'll begin by providing a brief background on logistic regression. So logistic regression is a statistical model for classification. The heart of the logistic regression model is the sigmoid function. That could be seen at the equation on the bottom left, and it takes in a weighted sum, in this case represented as z, and passes it through that function defined there. And this function has the nice property that it compresses the outputs between 0 and 1. And what this does is it gives us a nice probabilistic interpretation of the output. And what that representation is the probability of y, given with y being our class label, given x, which is our input vector, and theta, the learned parameters. During training, we define a loss function. In this case, it's common to use the binary cross-entropy loss function. And what this does is measure the difference in our prediction probability versus the true class label. And this gives us a way of measuring how well the current model and the current parameters fit the data. Throughout training, we take the partial derivatives with respect to the parameters in order to get the gradients. And with the gradients, we can calculate an updated value for theta. And the goal of this is to minimize the loss function, and this is done using gradient descent. And by updating those values of theta, we're continuing to minimize the loss function, which ultimately gives us a higher accuracy or some other metric, but better classifies the data. Next, I'd like to give a brief background on Bayesian networks. Bayesian networks are a type of probabilistic graphical model, and the dependencies are represented using a directed acyclic graph. The nodes represent random variables, and edges represent the dependencies among the variables. on the image on the right, we can see a simple Bayesian network that's comprised of 4 random variables, A, B, C, and D, and we can see the dependencies defined by looking at the edges between these variables. So in particular, we would say that B is dependent on its parent node A. And one of the nice properties of Bayesian networks is it gives us a compact way to represent the joint probability distribution space. And even more so, it allows us to reduce the number of parameters required to represent that probability space. So, for example, if we were to assume that A, B, C, and D are all binary variables that could, take on a value of, let's just say, true or false, it might take 2 to the n different parameters to represent that probability space. When we represent the data in this way, we can reduce that. Looking at the formula on the bottom right, we can see the probability of x, where x might be some inputs or the values that A, B, C, and D take on. Well, we can see that's actually just the product of that instantiation of that node given the parent node. And so this can completely reduce the number of parameters required to actually represent that probability space. Now I want to begin discussing the methodology for this proposed hybrid model. And to start, I'm actually going to go over what this model looks like at inference time. We'll later cover how this model is trained, but I think this will give us some intuition of the necessary components for training. So to start, we take a new input vector, and this might be on some unseen data after training. And these input vectors are used to instantiate the feature nodes. Given these new feature node instantiations, we can update the conditional probability tables of the weight nodes now that we have more information. Once we've updated the conditional probability tables, we need to infer what the weights should be. And so the weights are inferred using the most probable explanation. So in the conditional probability table, we're looking for the weight that has the highest probability given the instantiated value of the feature node. Given these weights, we can now pass them to the logistic regression model. And so now we can take the weighted sum, as we would do in normal logistic regression, and pass it through the sigmoid function and return a class label. So the image on the right is a basic flow diagram of what we just discussed. And as you can see, there's the input vector at the top. This really serves as the starting place, and that's used to inform the feature instantiations. We have a defined Bayesian network architecture, and we'll discuss a little bit more about how this architecture can be defined soon. From there, we use that Bayesian network to infer the weights. And then, again, following that, we use the same steps that we would normally use in logistic regression, where we calculate the weighted sum, pass it through the sigmoid function, and return a class label. So now that we have an idea of what this model looks like at inference time, we can spend a little bit more time discussing how to actually train this type of model. Now that we've covered the basic flow diagram of what this model looks like at inference time, I want to discuss how the model is actually trained. So to start, we have to define the actual Bayesian network, specifically the architecture for this network. So as a starting point, a super simple architecture was used where the feature nodes point directly to their corresponding weight nodes. And these weight nodes are initialized randomly. So the value of the weight in the conditional probability table is just given some default randomly generated value. then the probability of that weight, given the different values that the featured node could take on, they're all going to be assigned a probability of 1. We're going to discuss how this looks on the first pass, so how it looks when the model's initialized, versus the second pass when we actually introduce new weights into the system. So this process is updated in batches, and the first step is we infer the weights from the Bayesian network. So as we mentioned, this is done using the most probable explanation. Now on the first pass, there's simply one weight in the table given, and it's assigned a probability of 1. So we know what the weight's going to be on the first pass. So we infer those weights. Those weights are passed to the logistic regression model, and then the logistic regression model outputs the probability of y given, which is our class label, given x, our input, and theta, which is our learned parameters. That's normally what we'd get. The assumption of this study is that this is actually going to be proportional to the probability of the weights given x. And this is what we're actually storing in the Bayesian network. So now that we've actually passed some of these values through the logistic regression, we can actually update the values in the conditional probability table. So where we had initially assumed it had a value of 1, we get a more refined answer saying that no, maybe it's closer to 0.8 or 0.6. It's really whatever the output of the logistic regression model is. And so now we could update that value in the conditional probability table. Of course, this leaves us with a gap because there was only one value and it had a probability of 1, so we need to fill the missing probability in order to have it not violate any of the laws of probability. And one of those laws, of course, being that the probability is summed to 1. So, using gradient descent and using the binary cross-entropy loss function that is common to use with logistic regression, we could actually calculate new weights. This looks very similar to how a traditional logistic regression model works, except that now we're going to calculate multiple gradients. And the number of gradients is based on the different values in the conditional probability tables. So in the simple case where each weight node is only influenced by its input feature, we just have to calculate a gradient for each of the different values in the weight node, which is going to be directly correlated to the number of values that the feature node could take on. So we can calculate those separate gradients, and then we could use the same update rule in gradient descent to calculate a new weight. So given that new weight, we could introduce it into the system again. And so it's actually going to be put into the conditional probability table. And one of the choices used was to assign that probability to 1. So now that we've assigned it a probability of 1, we have to renormalize it in order so the two probabilities add together and sum to 1. So we can renormalize the data, or the conditional probability table, and now we've updated the Bayesian network. And so then this process would just continue again. We would collect a new batch, we would update, we would generate a new set of weights, and now when the weights are being inferred, there's actually two values in the in the conditional probability table. And so this process continues, the same steps, until it, in this case, the convergence criteria is really just an iteration count, but perhaps a future area of improvement is to have a better, more well-defined convergence criteria. Next, I would like to discuss more about the data set. But before diving in directly to the data set, I first want to discuss this concept of linear separability. Linear separability is when we have class labels that can be divided by a linear decision boundary. If we look at the images on the top here, we can see an example on the left where it is linearly separable and on the right where it's not. On the left side, you can see this is a simple two-dimensional case, and in this case, a single line can be used as a decision boundary that separates the two class labels perfectly. If we look at the image on the top right, we can see that there's no single line that would actually be capable of dividing this data into its appropriate class labels. And so when we're looking in 2 dimensions, we consider a line. When we would look in 3 dimensions, we consider a plane, and anything higher than 3 dimensions, we would look at a hyperplane. Similarly, for a number line representation, or one-dimensional, we're actually just looking for a single point that could divide the class labels. And this is a very important concept because this data set was specifically designed not to be linearly separable. As stated in the motivation of this research, logistic regression has trouble solving problems where the data is not linearly separable. So in order to provide a challenge for this new proposed hybrid model, we wanted a case where we knew logistic regression would fail, but perhaps this new approach can achieve that. So in order to do this, a toy data set was created, and the data set was created in such a way that it would be discretized into 4 bins, and if the value was 1 or 3, it would be given class label 0, and if it was 2 or 4, it would be given class label 1. And we could see this on the image on the bottom, where we have this alternating pattern between red and blue, which is the representation of the class label. And if you try, you'll find that you cannot put a single point that can divide this data into its appropriate class labels. You might put one at 2, and you would see that splits some of the points there, but following that, when you get to 3, you would see more of class label 0. And so there is just no way to do this. So the expectation is that logistic regression is going to get stuck in a local optimum here. Now we could begin looking at the results. So the model performance was assessed using accuracy metric, and accuracy is just the number of correct classifications divided by the total number of classifications. And so we can see that the hybrid model, which is on the top, achieved 100% accuracy on the training set, versus the logistic regression model, which is at the bottom, got stuck around 50%. And this is exactly what the research, and specifically the data set, aimed to do. We had already known, it was our understanding that logistic regression would not really be able to classify this data set that had that interwoven data pattern. But when we use the Bayesian network to inform what the weights should be, it's actually able to split that and find multiple decision boundaries and able to classify them. And so we can see that after just 18 iterations or so during the training process, it's able to perfectly classify this training data set. Now, it is important to note that because the data generated was completely deterministic, there was no held out validation set. Any validation set would have looked exactly the same as the training data because there was no inherent stochasticity in the data. And so there was no point of using a held out validation set. However, we'll see in the discussion section that this is a future area of research that we'd like to continue working on. Next, we'll begin looking at the results for the model runtimes. So here in the table, we can see the values for the hybrid model and the logistic regression, and these values are in seconds. And so over 5 runs with different seed numbers for each run, we could see that on average, the logistic regression model is roughly 2.4 times faster than the proposed hybrid model. Part of this is to be expected though, because the logistic regression model comes from Python's scikit-learn package, and so this model has been highly optimized. The hybrid model has not gone through similar scrutiny and remains unoptimized. So we would expect some performance improvements just by simply optimizing the code. However, even with that, it's still likely that the hybrid model is going to take an additional hit in runtime, and that logistic regression would be even faster than the currently acknowledged 2.4 speed difference. The reason for this is because every time as the network complexity increases, we have to calculate separate gradients for each of the combinations. And the single feature case that we use now, only 4 gradients were calculated. This made it less computationally expensive than as we increase the model complexity, or the Bayesian network model complexity, in which case we're going to need to calculate gradients for all the different combinations of the interwoven variables. There's a few additional points that I wanted to discuss from this study. First, I want to talk about the generalization on unseen data. So as mentioned before, when the accuracy metric was taken, it was done on the training data. And the reason that it wasn't done on a validation set, which is the more common way of evaluating models' performance, is because the data generated was done in a completely deterministic way. So as such, we wouldn't have seen any difference on the actual validation set. But this remains a pretty big knowledge gap in the performance of the model. One of the effects that we have not tested in this study, but would be very important, is to see if we're overfitting the data. I think that is something that there's a potential risk there. And so as such, we might need to introduce some regularization techniques. This would help prevent overfitting, but still giving the model more flexibility than logistic regression. Next, I want to discuss some of the limitations of the data set that was used. For starters, it was only done on a single feature, and this served as a good initial test case and gave a clear, concrete metric to test against, seeing if the hybrid model can overcome the limitations of linearly or non-linearly separable data. However, it's not really reflective of real-world data, and so we would need to extend the study and ideally find data sets with more intricate relationships between the variables that would allow us to define more interesting Bayesian network structures to infer the weights from. Additionally, it would be nice to include the handling of continuous variables. Right now, it assumes that the data has to be discretized. That doesn't necessarily have to be the case. So when trying to move to a place where it's working on real-world data, that is another step that can be taken. So the increased training time, while we touched upon it briefly before, just to highlight this point again, is that the increased training time will occur from these more complex relationships in the Bayesian network. As we have more relationships, there's going to be more gradients that need to be calculated to populate the conditional probability tables with new weights. And as such, we're going to take a hit in training time. Moving towards some more interesting and potential future research, opportunities and how this model can be further improved. I want to start by talking about the data imputation. So data imputation is how we handle missing data in our training set or in our data set entirely. And I think this structure offers a unique approach to data imputation. And actually, the proposition here is that you wouldn't need to impute the data. And the reason for that is in the conditional probability tables, we can leave space for unseen data. And depending on the relationships that exist in the network, that might update the conditional probability tables. And when we're using the most likely explanation to determine what the weight should be, we could actually just directly take into account that, hey, this variable did not have an instantiation. And so information can flow through the network to inform what those weights should be. I think this could be an exciting area of exploration, and to see if there's more value in learning what the weight should be when not seeing the data versus just assuming what the data would be, like for instance the mean or the mode, and just populating the data directly. Lastly, another interesting area that could further improve upon this is structural learning. So structural learning in Bayesian networks, exactly as the name implies, learns the actual structure of the network. So you could define a metric to which that determines how good the network structure is, and it continues to update itself and try to learn what the best structure is. Right now, in this coupled learning process for the hybrid model, it uses the same structure and assumes that the structure is predefined. I think an exciting opportunity in the future is to explore how we can incorporate structural learning into this coupled learning process, where we don't even have to explicitly define the structure of the Bayesian network, but instead using information that is passed from the logistic regression model back to the Bayesian network. It could continue to update the structure of the Bayesian network in addition to the probabilities that live inside of it. So, in conclusion, the purpose of this research was really to define a methodology for a hybrid model that can combine the strengths of logistic regression and Bayesian networks. In order to test this hypothesis, a toy dataset that was non-linearly separable was created. The expectation was that the hybrid model would be able to achieve 100% accuracy in classifying these data points, while the logistic regression model would get stuck in some local optimum. The results from this study show that this goal was able to be achieved. And while this only serves as an initial investigation into this hybrid model, I think the results of this study show that this area has some promise and that it is worth continuing the research and improving and refining this model. Some of those refinements had been discussed in the previous slide, and how we can take this model and move it to some real-world data sets and see the performance metrics there. I appreciate your time, and thank you everyone for listening. And I would be happy to try to answer any questions left in the comments. Thank you.